Hey everyone, let's do some curve sketching. This is a continuation, effectively, of section 4.3 when we learned about maxes and mins and concavity. We learned about the shape of a curve. Now we're just going to put that together with a couple of other little details that we may have even learned before calculus class, and we're going to sketch the curve. We're going to get its shape good, and we're going to get its location good. One thing that we're going to include when we sketch the curve are the asymptotes. Now recall from the beginning of the semester that a vertical asymptote of a function is a line, just denoted x equals c, where the left and right hand limits are plus or minus infinity. Also recall from section 2.6 that a horizontal asymptote is a horizontal line such that the infinite limit, or I should say rather, the limit as x approaches infinity or negative infinity equals a certain value, right? Infinity does not count, right? It has to equal a real number. So to sketch a curve, here's what we do. We find the domain, which is the stuff that you're allowed to plug into the function. So I'll say all x values, I should say, maybe I'll say we can plug into f. Then we find all vertical and horizontal asymptotes, right? Note that this stuff right here is not calculus, really. I guess the horizontal asymptotes, the asymptotes are a little bit calculus, right? You're taking some limits, but basic limits. It should be basic limits. Here's where the calculus really happens, though. That's when we start taking derivatives and second derivatives, right? Then we sketch the curve. Let's start off with example 1. Sketch this curve, right? And then we'll just say let y equal f of x, which equals x minus 4 over x plus 1. All right? So first off, we're going to just follow the list, right? Find the domain, right? Remember the list, right? Find the domain, find the asymptotes, intervals of increase, decrease, intervals of concavity, and then we're done, right? So first off, f has domain. Now remember, the domain is all the stuff that we're allowed to plug in to f. Well, if you notice, that's everything except negative 1, right? Because we'd be dividing by 0 in that case. So what we're going to say, you can write this two different ways. You can write negative infinity to negative 1, union negative 1 to infinity. You could also write r minus negative 1, right? I'll typically write it in interval notation. I think it's more familiar. Okay? So that should usually be a pretty quick thing to see. Next up, we're going to find the asymptotes. Right? Now, since we are potentially dividing by 0, we are going to have some vertical asymptotes. So I'm going to write VA for vertical asymptotes, and then just take the left and right hand limits, right? The left hand limit, right? Limit as x approaches negative 1 on the left of x minus 4 over x plus 1. And again, there's no real technique here. You just have to figure out. The top is going to negative 5. That's a negative. The bottom is going to 0, but it's always going to be negative. So we have a negative over a negative. It looks like our answer is positive infinity. We're also going to have that the limit as x approaches negative 1 from the right of our function here is going to be negative infinity, right? Same thing, top is approaching a negative, but the bottom is approaching a positive. Okay? So we should just write here, f has, maybe I'll write it down here actually. F has VA x equals negative 1. Now note that we knew this before we took the limits, but it's still good that we took the limits because now we know the behavior around x equals negative 1. Now over here, I'm going to write HA for horizontal asymptotes, right? And here we take the limit as x approaches infinity of f of x, right? And what do we do here? Well, we're just going to multiply the top and the bottom by 1 over x. And what do we get? We get 1 minus 4 over x over 1 plus 1 over x, and we see that that equals 1. I will leave this as an exercise to you, but you can also show that the limit as x approaches negative infinity of x minus 4 over x plus 1 also equals 1. Again, I skipped the work for that. So here we can say, so f has horizontal asymptote y equals 1. Again, note that vertical asymptotes are x values, horizontal asymptotes are y values. Now, we're going to put this all together. Or sorry, I shouldn't say we put it all together. Not doing that yet. Now we're going to switch gears and do the calculus stuff, right? So we're going to find maxes, mins, intervals, increase, right, critical points, blah, 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 blah. So we're going to take the derivative, f prime of x, and maybe I should even say let f prime of x, and then we take the derivative, and then we write equals 0, okay? Actually, I think we got a bit of space, so maybe I can space this all out a bit more. Space this all out a little bit more, right? Okay. So anyway, let f prime of x, which equals low d high minus high d low all over low squared. We're going to let that equal 0, but first we're going to simplify it. You always want to simplify it, right? So we have x plus 1 minus x plus 4. Be careful of that negative sign. All over x plus 1 quantity squared. Right? And then if we simplify that a little bit more still, we're going to get 5, I believe I'm doing this correctly, 5 over x plus 1 squared. Let that guy equal 0. Do you see anything that's a bit off about that? But f prime of x never equals 0, right? There's a 5 in the numerator. Not only does it not equal 0, f prime of x is always greater than 0 when defined. Also note, f prime does not exist, or maybe I should say f prime of x, at x equals -1. And that should be obvious because -1 wasn't in our domain for f. Okay? So now, normally you would do your interval chart or whatever, but again, I'm going to go right on to step 4, which is the second derivative stuff. And I'll write all the things there, right? But it is worth noting, perhaps, that f has no critical points. I'm not going to do it because the problem didn't ask for it. All right? Step 4. Let's say, I guess here we'll say let f double prime of x equal 0. Right? Well, at this point, I think we can actually just take that derivative, right? I think it's going to be -10 over x plus 1 quantity cubed equals 0, right? Let's just see how we get that derivative. Except, hold on a second, f prime of x never equals 0. Right? It doesn't equal 0. Okay? Also, f double prime does not exist at x equals -1. And again, that should be obvious because neither did f or f prime. Okay? So, what do we have here? Well, we have our interval chart. Right? So all we have here, maybe I can get rid of that, right? All we have are the following. We've got, I guess it's -1, right? And what's happening? Well, for f prime, remember, f prime we said was always greater than 0 when defined. Now, f double prime's a little more complicated than that, right? Plug in -2, right? We get a negative on the bottom, right? So we have a negative over a negative, so it's actually positive. Plug in 0, you get a negative, right? So that's our interval chart. So now we want to write a bunch of stuff, and then we want to finish off by sketching the curve. So f is increasing on -infinity to -1, union, -1 to infinity. It's never decreasing, but I'm not going to bother writing that. It has no local max or local min. I'm not going to bother writing that. And is concave up on -infinity to -1 and concave down on -1 to infinity. Okay? That's all we have to write in this case. Normally we'd write a bit more. We'd have critical numbers or critical points or maxes or mins, but we don't need to write that because we don't have any in this situation. So last but not least, we're going to sketch the curve. So one thing to keep in mind is that when we draw this interval chart, we understand the shape of f. Because when we have a curve that is increasing and concave up, we know that that looks like this. And when a curve is increasing and concave down, we know that that looks like this. So all we're going to do is put those shapes together. Now the question is where? Well, we know that we have a vertical asymptote, x equals -1. Right? Right? We also know that we have a horizontal asymptote, y equals 1. Right? So with these constraints, we want to sketch our curve. So looking at this, I think we see our curve is going to do something like that, and then something like that. And that is our curve, y equals f of x. Okay? So that's how you sketch a curve. Let's look at another problem. Sketch the curve y equals e to the x squared. Right? Another example. All right, I guess maybe before we do step 1, let's just say let y equal f of x equal e to the x squared. So that if I talk about f, we know what I'm talking about, right? All right, so step 1, f has domain, and you can write either negative infinity to infinity, that's what I'll write here, or you could write r, right? All real numbers. Okay, done. Number 2, you should be able to see very quickly whether f has vertical asymptotes or not. Right? No vertical asymptotes. For horizontal asymptotes, you might be able to eyeball it, but I'm going to want you to take the limit as x approaches infinity and negative infinity. And I think you can just see by looking at this that we're going to get an answer of infinity. And similarly, let me just get that too, right? It doesn't matter whether we're approaching infinity or negative infinity, right? X is getting squared. We're blowing up, right? All right, so we have no vertical asymptotes, we have no horizontal asymptotes, right? Because we took the limits at infinity, we did not get a finite answer, okay? Now let's take the derivative, right? So here, remember, we're going to let f of x, or sorry, we're going to let f prime of x equal 0. Well, the derivative is going to be e to the x squared times 2x. Well, I think we can see that 2e to the x squared never equals 0. So the only thing that could equal 0 is x. So our critical point, we have a critical point, so maybe I'll say f has critical point 0, 1, right? Because e to the 0 squared is 1. Anything to the 0 is 1, right? All right. Now, at this point, I'm going to go on, right? Again, you can draw the interval chart if you want, but I'm going to just go on to the second derivative stuff and do the interval chart toward the end, okay? Step 4. Now we're going to let f double prime of x equal 0. So remember that we have e to the x squared times 2x. So that's going to be, it's a product rule, right? E to the x squared times 2x. That was the derivative of the first part, and then we left the second part alone, right? You see what we did here? We took the derivative of this guy, left that guy alone. Okay, pause the video for a sec if you don't understand that. Anyway, that was the first part. Then we do plus, and now we leave e to the x squared alone. And then we take the derivative of 2x, which is 2. All right, again, that there. Right? And we let that all equal 0. Well, let's see what that gives us, right? If we factor out a 2e to the x squared, we get 2e to the x squared. 2x squared plus 1 equals 0. Well, if you notice this, you might notice that actually that never equals 0, right? Right? In fact, it's always greater than 0. Let me write that, greater than 0. How about that? All right, so anyway, we get something that's greater than 0. Okay, so let's see what we've got. So I guess that means f double prime never equals 0. It always exists, right? Okay. Okay, then. I guess we're drawing our interval chart. Right? So we draw our interval chart. We don't really have anything to say for f double prime. For f prime, we do have a critical number, right? 0. We always want to write that. And now we just go back to f prime, right? Plug in a point, plug a number into f prime. And if you plug in a negative, I think you see you're getting a negative. And if you plug in a positive, I think you see you're getting a positive. So we get that. So f is decreasing before 0, increasing afterwards. F double prime, all we need to do is plug in any point, right? And we see that we always get a positive number. Okay? Well, let's try to draw that a little better. Now all we're going to do is sketch the curve. We have no asymptotes to worry about. We have no holes or anything to worry about because our domain is all real numbers. We have one critical number to realize, that is, or to recognize, to point out, right? That is 0, 1, and it's a minimum. Oh shoot, I'm sorry, I forgot to write in words what our graph is doing. Let's move this down and quickly write it here. F is increasing on negative infinity to 0, and oh, sorry, f is decreasing, my bad, and increasing on 0 to infinity with local minimum f of 0 equals 1. F is concave up everywhere. All right? That's all there is to say. There's no inflection point or anything, right? So anyway, we have this. We have a function that is always increasing, or sorry, that is always concave up, it is decreasing, and then it is increasing. So our curve looks like this. And that's something, in fact, it's even narrower than that. It's like that. Right? So that's what we've got for that. So that's how we sketch a curve. I think that might be, yeah, we're not going to do that last. Let's do one more example, maybe a little more involved. I'll leave the last one to you, right? Sketch this curve. Again, we're going to let y equal f of x. And that's going to equal x minus 1 over x squared. So here, what's the domain of f? F has domain, do you see? Everything except 0, right? Because if you plug in 0, then you're dividing by 0, right? So, everything but 0. All right, next up, asymptotes. Well, since we're dividing by 0, we're going to have a vertical asymptotes. So f has vertical asymptote. Maybe I'll write it first, x equals 0. But I still want us to be taking limits, right? Limit as x approaches 0 from the left of f of x. I'll just write this out. Let's see. The bottom is always going to be positive. But you see that the top is going to be negative. So we have negative infinity. Okay. So we have that. For horizontal asymptotes, we take the limit as x approaches infinity of x minus 1 over x squared. And maybe you can see this. Even if you can eyeball it, I still want you to do it all out. Well, I just write x. And that's going to equal 0. And again, similarly, I'll leave this as an exercise for you. But it's the same as x approaches negative infinity, okay? So, f has horizontal asymptote, y equals 0. Okay, good to know. Now let's go on to the calculus, right? We're going to let f prime of x equal 0. Maybe I'll say let f prime of x equal 0. And then say down here, f prime of x equals, so right, we've got, maybe I'll just write over here so I remember. So we're going to get low d high minus high d low all over low squared. And then when we do it out, we get x squared minus 2x squared plus 2x. Minus 2x squared plus 2x on the top. We get x to the fourth on the bottom. Do it out again. We get, it looks like we get 2x minus x squared on the top. We get that on the bottom. And then note once more, we can factor this into x times 2 minus x, right? So f has critical numbers x equals 0, x equals 2. Yeah, x equals 0 and x equals 2, right? Because x equals 0 when x equals 2, and it doesn't, yeah, right, because f prime equals 0 at x equals 2, and it doesn't exist at x equals 0. Okay. Let's just point out that f of 0 does not f prime of 0 does not exist. F prime of 2 equals 0. F of 0 does not exist. F of 2 equals 1/4. All right, step 4. Oh, running out of room here. So note that f prime is really just 2 minus x over x cubed, right? You can cancel out the x down there, okay? Let f double prime of x equals 0. Okay, so we're going to get, I'm going to leave this space over here for curve sketching. Let's see if we can make this happen, right? We're going to get low d high minus high d low all over low squared. And when we simplify that, yeesh, nothing super pretty. We're going to get negative x cubed minus 6x squared plus 3x cubed all over x to the sixth. And that equals 2x cubed minus 6x squared all over x to the sixth. And then at this point, let's factor out an x squared. So we get 2x minus 6 all over x to the fourth. And we're going to let that equal 0. And I think you can see that equals 0 at x equals 3. Looks like we're going to need an extra page, and that's okay. Probably, right? So let's see. So f, actually, before we do that, we really should write our interval chart, right? So write f prime, f double prime. We have a couple of values here, right? We've got 0 and 0, and we've got 2 over here and 3 over there. So let's see what that's going to give us, right? Before 0, f prime is going to, let's see, if we plug in -1, the top is positive, the bottom is negative, so we get that. If we plug in 1, we get positive. If we plug in like 3 or something, we get a negative over a positive, we get a negative, right? So we get something like that. For f double prime, let's see, if we plug in a negative number, then we get a negative. Plug in 1, we actually still get a negative. Interesting, right? Oh, wait, hold on a sec. Sorry, I lied. We plug in a negative number. Let's see, wait, hold on a sec. You plug in -5. You get a negative on the top, a positive on the bottom. Nope, sorry, you get a negative. Right, the bottom's always positive, right? You plug in a positive, like, 1 or something, and you actually still get a negative. But if you plug in a big positive number, then you get a plus, all right? So let's just write what we've got here. F is decreasing on -infinity to 0, union 2 to infinity, and increasing on 0 to 2. F has local maximum f of 2 equals 1/4. Right, that's a way of saying, look, you've got a maximum at 2 and it's 1/4. F is concave down on, now don't say -infinity to 3. That's not quite right. It's -infinity to 0, union 0 to 3. And concave up on 3 to infinity. And is there an inflection point? Yes, there is. It's going to be 3 comma f of 3, right? Because we go from negative to positive concavity. 3f of 3 is 2/9. Just to be clear, that is 2/9. All right, and because I don't have the space here, I'm going to have to just go on to this page. Sorry about that, guys. So let's just recall what we have, right? We've got vertical asymptote, x equals 0. Horizontal asymptote, x equals 0. All right, so we do that. Just to be clear, this is our x-axis. This is our y-axis, right? Let's see what we've got going on here, right? Before 0, we've got a curve that looks like this. But remember, we've got to respect and obey our asymptotes, so it's something like that. Let me try to draw that a little bit nicer, right? Something like that. Okay, we've got that. Then we're increasing, but concave down from 0 to 2. Let's maybe mark that. Right, so we're going like this. And then, well, what did we say our inflection point was? 3 comma 2/9. Our critical point was 2 comma 1/4 was our point, right? So we've got a point here, and then 2/9 is actually a little bit less, I guess. So we've got a point here and a point there. It's kind of weird, but we've got something that looks like this. So a couple of subtleties that we might not have seen if we did just the stuff from 4.3, right? Maybe we would have seen it, but without our asymptotes, we wouldn't have realized that we were hugging the x-axis so much. All right, now this last guy is a little bit more involved. I'm going to leave that to you to try, and we will stop there. There's a whole bunch of other practice problems over here. I'd also like you to try them, but I'm just counting these as part of guided practice.